Hi, this is Professor Ansaldi. I'm going to get you prepared for our work on Wednesday on section 2.2, which is going to be talking about derivatives of polynomial functions. Now, the simplest kinds of polynomial functions are constant functions. So remember, a function is constant if it just equals a single number. So our goal is if we are given that f of x is equal to c, we want to find f prime of x. So before we look at this, we can think about this intuitively by using Desmos. So let's switch over to Desmos and look at, for instance, the graph of y equals 2. So if I look at y equals 2, of course, it's just a horizontal line. So the slope is 0. So our intuition says that the answer we get when we use the limit definition should be 0. So let's go back to the notebook for a minute. So now, of course, we have this nice intuition, but this isn't a rigorous answer here. So anytime we ask you to do something, we want to do it using the limit definition before we develop the rules. So let's use the limit definition of the derivative to say that if f of x is a constant, so that means just a number, think 2 for instance, we want to find f prime of x. Our intuition is that this should be equal to 2. So we know by the limit definition of the derivative that f prime of a, or f prime of x, doesn't really matter, is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, here it's not too bad to do any of these simplifications because, okay, f of x plus h. How do I find f of x plus h? Well, I'm going to plug in x plus h in place of x in my function definition. Well, there are no x's over here, so when I plug things in, I just get c because there's nothing to replace. F of x, yep, that's still c. And so I divide by h. Again, if you're getting confused, think about a specific number like c equals 2. Now, when I do this, I get the limit as h approaches 0 of 0 over h. Well, 0 over anything, again, h is a number that's close to 0 but not equal to 0. So this number is the limit as h approaches 0 of the constant 0, and the limit of a constant is that constant. So we got the 0 that we expected. So from this, we conclude that if f of x is equal to a constant, f prime of x is equal to 0, just like we saw from the graph. So now, here's your first exercise on your warm-up on infinity. I want you to find the derivative of the function e to the pi. Now, if this looks hard, go to Desmos and put in e to the pi, power pi. So I want you to find f prime of x. The answer to this is your answer on Desmos. All right, so that's one of our first rules. So our second rule is the sum rule or the difference rule. So what does the sum rule say? So the sum rule says that if f and g are both differentiable, then their sum, f plus g, is also differentiable. And maybe you have a minus there if you're using the difference rule. And furthermore, how do we find it? Well, we just look at each part separately. So if I want to find the derivative of f of x plus g of x, this is equal to the derivative. So this notation means the derivative, taking the derivative of a function. I don't know if we've used that notation before, plus the derivative of g of x. So to put this in prime notation, this says f plus g prime of x, a quantity, is equal to f prime of x plus g prime of x. Okay, so let me show you this with two functions in Desmos. So I'm going to clear this one. So I'm going to look at the function y equals x squared, which we know something about the derivative. We've seen this a lot of times. And we look at the function y equals 3x, which is of course a straight line. So let's look down at the point 1. So we know at the point 1 from stuff we've done in class, the derivative of the blue function is 2. So we've seen that formula in class that the derivative of x squared is 2x. And so when we plug in x equals 1, we get 2. Now at y equals 3x, our derivative is 3. 3 times 1, or 3 times anything, it's always 3. So what would we expect the derivative of the sum of these two functions is? Well, we should get y equals x squared plus 3x. So what we expect is we get a slope of 3 plus 2, which is 5. And okay, zooming at the purple function, when x is equal to 1, let's see if I'm at the right spot here. That's a half, so we're actually way up here. Yeah, if we look, it looks like we have a slope, it's locally linear, and it seems as if we go up 5 here, we're going to start here, go up 5, and we go over 1. So it looks like, yeah, when we zoom in a lot, we get a slope of 5. So I'm not going to go through the limit definition of the derivative for this, but we have seen that the derivative of f plus g prime of 1 is equal to f prime of 1 plus g prime of 1, where f of x is equal to x squared and g of x is equal to 3x. So we assume that's also going to be true in general. So to prove this, you use the limit definition. The second rule, and again, I'm not going to go through the proof of this, is called the constant multiple rule. So what the constant multiple rule says is it says if c is a constant and f is differentiable, then the derivative c times f of x is equal to the constant times the derivative of f of x. Again, I'm going to write that in prime notation since we're just getting used to this ddx notation. So the derivative of the function c times f of x is equal to c times f prime of x. So we can pull out the constant out of a derivative. Now, for instance, let me give you an example. So if I have the function f of x is equal to x squared, and I let g of x be the function negative 2 times x squared, then the derivative of g prime of x is equal to negative 2 times the derivative of x squared, which is negative 2 times 2x, or negative 4x. Now, let's think about this in terms of rate of change. And again, the formal proof uses the definition of the derivative. But if we want to think about why constant multiple works, well, the derivative is the rate of change of f of x. But if I multiply f by a constant c, that will change the rate of change by c. So if f goes is twice as big, then the rate of change of f is also twice as big, for instance. And this would also work for negative numbers or fractions or any number we like. All right, so that's our intuitive notion. If you want to see the proof of the derivative, come talk to one of your professors or look it up in the book. And it's actually, you can actually do these by hand, I'm sure all of you. So then finally, for our final exercise, what I'd like you to do is I'm going to tell you that if f of x is equal to x cubed, the derivative, we'll see why in class, is equal to 3x squared. I actually did this one in class one day, and now I want you to find the derivative of the function g of x is equal to 4, let me make that a little neater, x cubed minus 3. All right, that's all for today. So go on to infinity. The other thing to remember is that we'd like you to finish the worksheet from class on Monday and turn in those answers on Wednesday in class. All right, have a great day, and we will see you all on Wednesday.